Hello, so I'm here to mark this week's exam with you. The exam's on conservation and dissipation of energy. The first question is about lots of energy transfers that take place in a house, and you've got a little diagram there to explain them. You've got a choice of words to fill in gaps in sentences in this box. A little trick which is really helpful is to cross out the word once you've used it. Or make a little note by it. It says you can use them more than once, but just something to bear in mind. Okay, so first question, you can see that I'm just using a cover sheet to reveal answers bit by bit. The gas boiler contains gas. Funnily enough, gas is a fossil fuel. Fuels and also fossil fuels have stores of chemical energy, large stores of chemical energy, and they are often transferred into a thermal energy store of another object by heating. So you would have gas which is heated up, then that allows the chemical energy, the energy in the chemical store, to transfer to the thermal energy store of, you know, radiators or water in the house. So that's your first answer there. Second one, we have water falling in the shower. So water would be suspended above the ground or the base of the shower, and it would have gravitational potential energy. Anything that's above the ground has gravitational potential energy. As it falls, it is going to be transferring well, the gravitational potential energy store of the water is going to transfer into the kinetic energy store of the water. That's happening by a force. It's the force of gravity in this case. Next.
So, energy is transferred as light waves from the surroundings, energy is transferred as light waves from the surroundings and are transferred to thermal energy store of the solar panels. So obviously the light waves are coming from the sun to the solar panels on top of the house, and then the thermal energy store of the solar panel is increasing, so that can be used usefully for heating water and things like that. That happens by radiation or waves. And I've just made a note of the transfer mechanisms on the side here. They're useful to have down because you want the initial store, the final store, and the energy transfer mechanism, you know, in any kind of energy transfer you're talking about. Alright, let's move on. So there's just one final energy transfer to talk about. The ceiling fan is switched on. Some energy is transferred usefully to the kinetic energy store. Other energy is transferred wastefully as sound waves. Obviously, you do not turn a fan on to make a noise. You turn it on to move air around and cool you down. All right. So next question is a calculation question. That means you should be bugging it. You're boxing the power because that's what you want to calculate. The energy, then I've put a slash there for work done, because work done is equal to the energy transferred. I'll come back to that in a moment. I've underlined that because we've got a given value there, and I've underlined the time, which is 20 seconds. So I've noted down here the three values, listed values on the side. I've written E and then just made a note: energy transferred equals work done. So energy or work done is 4,500 joules. So we've got a time, we're trying to calculate the power. The equation we can use is power equals work done, or energy transferred, divided by time. So that's 4,500 divided by 20 to give 225 watts. Watts is the unit for power, and I've just written that down there and used the capital W just to shorten the word watts. Alright, let's carry on. So this is quite a good question. I like this one. It gets you thinking about a particular experiment and thinking in a scientific way. So it wants you to plan an investigation to find out how much a lamp affects the temperature of surroundings in 5 minutes. You're given 4
4 different lamps. You can see one of the lamps being used there, and you're given the first step in the investigation. So first step is set up the apparatus using lamp 1 and take the starting temperature of the thermometer there. You can see a close-up of the thermometer here. The second step would be to record the temperature rise on the thermometer after 5 minutes. So if you've read the question carefully, you'll see that it wants you to do it for 5 minutes, okay, and you'd measure the temperature rise and record that. The second step would be to repeat using lamps 2, 3 and 4, right? So the idea here is you're changing the lamp to work out which lamp has the greatest effect on the temperature of the surroundings. So you want to test each lamp with the same conditions to find out what the temperature rises are. The last point is that you want to record your results in a table. The reason we record our results in a table is to make things as easy to analyse as possible. We can clearly see the results and see which lamp has the greatest temperature rise. Okay, so this is where things start to get So
it wants you to give the independent variable. Remember the chime mnemonic. You change the independent. Alright, so the thing we've changed in this experiment is the lamp. There are 4 different lamps that we've used, so the independent variable is going to be the type of lamp, and I've written that there. Then the dependent variable, remember you measure the dependent variable, and the thing we've measured, have a think about it, we've measured the final temperature, or I would accept it, change in temperature, or temperature would still be good enough to get you the mark. Okay, why is it important to measure the height of the lamp? Okay, quite a long answer for this one actually. It's to keep the lamps at the same distance, because if you had lamps at different distances away from the thermometers, you would get readings which would be different, and actually this is a control variable. So you want to keep the lamps at the same distance. So lamp 1, lamp 2, lamp 3 and lamp 4, they're all positioned at the same height above the thermometer. That makes it a fair test, and we call it a control variable. Okay, a calculation question on efficiency. So make sure you're bugging. The 18,000 joules is the total energy. The 13,320 joules is the useful energy. He wants you to calculate the efficiency, so I've boxed that. I've then listed values here. So useful energy, waste energy, the efficiency we don't know. Remember, efficiency doesn't actually have any units, so I've just made a note of that there. So we're doing the useful divided by, excuse me, I've written wasted there, I should have written total. The useful divided by the total equals 0.74. It doesn't ask for percentage efficiency, so you don't need to times it by 100. If you did, that's okay, but 0.74 with no units would be enough to get you 2 marks there. Right, I'm going to pause this video after the next question, and then there'll be a second part. So it wants you to describe the useful energy transfers when lamp 2 is switched on. So you want the initial and the final store, and then the transfer mechanism as well. So the initial is going to be the chemical store of the fuel in the power station, because all our electricity comes, or the vast majority of it comes from power stations which are burning fossil fuels to release or to transfer energy into thermal energy stores of water. They then boil that water. That drives a turbine and a generator, and electricity is released from the generator and transferred to our homes, and the final store is going to be the light waves, and there's also some thermal energy as well. That's in brackets because it's wasted energy, and that's done electrically. Alright, so that's the energy transfer mechanism. Right, I'm going to pause the video there and come on to the second part.